I'm sure that you've all seen one of these before. This is called Newton's Cradle, but I'm not sure why. Anyway, it consists of 5 pendulums made from fishing line and steel ball bearings. The point of this toy is to draw a ball backwards and let it collide with its friends. I know we are currently studying energy, but the best kind of physics to study collisions with is momentum. Let's start there. Momentum is conserved. If I draw one ball out, it will hit the other balls with a momentum of mv. That quantity, mv, must be conserved. All the balls have the same mass. One ball comes out with the original ball's speed, v. If I draw out 2 balls, 2 come out after the collision. Even though there are only 5 balls, if I draw out 3, 3 come out after the collision. If I send in 4 balls, 4 balls come out. Here's my favorite, 5 in and 5 out. I like it because it doesn't make that annoying noise. Let's recap this mathematically. Momentum is conserved. When 1 ball goes in, 1 comes out. When 2 go in, 2 come out. Here's a different scenario. Can you interpret my math? In this line, I'm suggesting that we send 2 balls in, but get 1 ball out, moving at twice the original ball's speed. Mathematically, 2mv is equal to m times 2v, right? Do you think it'll work? Let's try it. No? Nope? Well, if it's not happening, there must be a reason for it. That reason has to do with conservation of energy. These balls are elastic. When they collide, they do not change their shape. Since no work is done in deforming the balls, the kinetic energy in the system should be conserved. That works if we send 1 ball in and get 1 ball out. It works if we send 2 balls in and get 2 balls out. However, look at this. It does not work if we try to send 1 ball in and get 2 balls out. That is why we never see this happen. While we're at it, let's watch the behavior of this toy over a longer time interval. When I pull a ball backwards, I'm doing work on it. As I hold it in this position, that work has become gravitational potential energy. When I let it go, that potential energy becomes kinetic energy. On each cycle, the energy switches from potential to kinetic and back again. That original energy I gave the system as work, pulling the original ball back, stays in the system. Or does it? You can observe that the balls are not going as high anymore. This is actually not a closed system. On each cycle, the ball experiences friction as it moves through the air. When the balls hit each other, they make a noise, they heat up, and they vibrate the strings that they're attached to. There is one more idea we can explore with this system. We said that the initial momentum of the first ball is equal to the final momentum of the ball that comes out the other side. And it is, initially. But then that ball turns around and comes back the other way. Momentum is a vector. How can that momentum change all by itself? It can't. The balls are not isolated. As the ball comes out of the collision, the tension in its string acts to give it an impulse that gradually changes the magnitude and direction of the ball's momentum. Another way to see that is to consider the toy in its relation to the table it's sitting on. Before I let the first ball go in, the total momentum in the system is 0. That means that the total momentum at all times must be 0. We will only see that if we include the table in the system. As the first ball goes forward, the table must go backwards. When the ball at the other end starts going backwards, the table must go forwards. Let's watch that happen.